Hello everyone, welcome to a physical science lesson. We've got a really exciting topic for you. It's the topic of electrodynamics. Now, this topic is broken up into two different sections that we're going to focus on. Today we're going to focus on the motor effect. So come, let's go and have a look and see exactly what we're doing. So when we talk about electrodynamics, the one thing we need to start with is consider how many different ways that we use electricity. You could think about that and say, well, there's lighting, there's heating, but you know what? There are a whole lot of other ways as well, and those involve motors and generators, electric machines. And in fact, if we didn't have this theory about electric machines, electrodynamics, we probably wouldn't really have used electricity too much. But it's the breakthroughs that we found in the use of electrodynamics that's really changed the world. So have a big picture look at what we're going to be dealing with over our discussion on electrodynamics. So when we deal with electrodynamics, there are really just two areas that we're going to be talking about: the electric motor as well as the generator. And these two machines operate more or less with the same components, but they operate differently. And the crucial issue is what energy transfers are involved. So when we're dealing with an electric motor, we take electrical energy and we produce mechanical energy. And that is an important idea that we're going to be dealing with. We recognize in both of these situations, we're going to be dealing with a force, a current that's usually in a coil, and a magnet. And we're going to try and put those ideas together. So we've got a very good idea both of how a motor works and how a generator works. But our focus for today is on the electric motor. So let's get right into it. When we deal with the electric motor, we need to remind ourselves on some previous terminology that we've dealt with. The idea of a magnetic field, the idea of magnetic flux, and electromagnetism. And I also want to remind you about the right-hand rule. Now, these factors we've discussed when we dealt with electromagnetism. So just let's revise some of that by looking at the concept map on electromagnetism. Do you remember electromagnetism dealt with electric current being able to produce a magnetic field? And we recognized that could happen if there was a current passing through a straight conductor or a loop or a coil, a solenoid. We also represented current and the magnetic field in different ways. If you remember, we represented with a cross to say that was current that is moving into the plane. With a dot, it tells us that current or the magnetic field is moving out. We're going to use the same symbols when we're dealing with motors and generators. So it's important that you revise those. Remember, we also dealt, when we were dealing with electromagnetism, with the idea of electromagnetic induction. And in this case, we did the converse. In other words, we said, let's take the magnetic field and let's see if we can produce an electric current. And so in that way, we're doing a similar thinking skill. We're going to start by looking at how current passing through a coil can produce motion. And then we're going to turn it around and we're going to say, if we have motion of a coil in a magnetic field, we're going to be able to produce electric current in a generator. So these things you've got to get clear in your mind, and you've got to make sure that you separate out and be very careful that you don't get confused. And that's why we're going to take it step by step. So the first thing we're going to look at is, what is an electric motor? Well, it's a device that converts electrical energy into mechanical energy. When we talk about mechanical energy, we're really talking about movement. So we're saying, let's pass an electric current into a conducting wire or a coil, and let's place that in a magnetic field. Let's see what the effect is going to be. Well, it shouldn't surprise you that when we have a current-carrying conductor, around that current-carrying conductor, there's a magnetic field. And if we put a local magnetic field into a stronger magnetic field or a permanent magnetic field, there's going to be some sort of force or interaction. Well, let's see exactly how we're going to describe that and make some predictions. So, here we have a very simple situation. We've got the north end of a magnetic field, or of a magnet, and the south end of a magnet. And we know that between these two, there is a magnetic field that will run from the north to the south. And so we can draw that in from the north to the south. But we also recognize that we can use our right-hand rule to show the magnetic field around the current-carrying conductor. Now, do you remember the right-hand rule? Remember, I'm going to put my left hand away, put it in my pocket, and I'm going to use my right hand. And the right-hand rule says, if you are taking a single conductor, then point the thumb in the direction of the current. And then the field lines will be the curl of the fingers. So in this case, remember the cross means going into the board. So in that orange-colored copper conductor is the direction of my thumb. My thumb is going in. And over here, I'm going to see that the curl of my fingers goes in a direction that is clockwise. So around this conductor, there's a magnetic field that goes clockwise. We know that magnetic fields can't overlap each other. They can't cut across each other, but they can tend to have a pressure on each other or change each other. And so when we put that drawing together, you will see that in this region, it looks like they're opposing each other. And in this region, they're reinforcing each other. They're in the same direction. So I'm going to redraw the field pattern of this combination to show you what the effect is. And so let me erase what I've got on the board and let me put in the field line pattern that I want to show you overall. So overall, we know that it's going from north to south. This one gets bent. This one is reinforced on this side. And so we can carry on, and eventually we can draw that one. In all these cases, the direction is from north to south. And so we have this really strange looking pattern that's kind of skewed on one side. There's a gap on the other side, because we can kind of think of it as the magnetic fields sort of cancelling each other out, working against each other. They've actually bent each other. And so the end result is that we've got a really strong magnetic field. Field lines are together over here, and there's hardly any magnetic field over there. That's created an imbalance. And nature doesn't like an imbalance. And so what happens, because of this tension and because of this bent magnetic field, there is a force that is exerted on that conductor. And that force is going to try and exert in a way that will straighten the magnetic field. And so we can expect that there will be a force that acts on that conductor, if it's free to move, to push it out of the magnetic field. And what will happen? The field will be restored. It will be back to its straight form, and the conductor will be quite independent. It will be fine. This process of a force being exerted on a single conductor is known as the motor effect. And it was the initial thinking of a man called James Fleming. And Fleming kind of started to build motors because of this observation. And we will see a little later how he actually invented a rule to predict the direction of the force. So the force would be in that direction because we're trying to straighten up and to keep the field constant and keep it nice and straight and keep it in balance. Let's just have a look at one more scenario. If the direction of the current was changed and the magnetic field is still the same direction, what do you think is going to happen? In which direction is the force going to be on this conductor? Notice the current direction has changed. The field is still the same, but now it wouldn't be much to think that perhaps the force is going to be in the opposite direction. Let's confirm our thinking. If we took our right-hand rule and we recognize the current is coming out of the board, the thumb is showing the direction out, the curl of the fingers in this direction, over here it's going to oppose the magnetic field coming down. So if I draw the field line pattern, then what we'd recognize is the field line pattern is going to do something like this. And as you might guess, because of that bend in the field line pattern, going from north to south, there's going to be a force that is going to be indicated in that direction. And so that free-moving conductor is going to be pushed out of the field, and we're going to find that the field is restored to what it usually was. So please make sure that you practice that idea, but we'll try and introduce a shorter cut to this explanation by looking at both Fleming's left-hand rule and another rule. But you know what? I think it's time for a little break. So you go for a break and we'll be back to explore the motor effect in a little bit more detail. Welcome back, everyone. We've been investigating the idea of electrodynamics, and we're taking a closer look at the motor effect. In particular, we've been able to see that there's a relationship between current, the magnetic field, and a force. So let's just make sure we've got those things sorted out. And so as we look at our concept map, we'd recognize that when we're dealing with the idea of a force, we often use the symbol F. When we're dealing with the magnet, we're dealing with a magnetic field, we use the symbol B. And when we deal with a coil or current in a coil, we deal with the symbol I. Now, I've written it properly in the wrong order there, but F, B, and I go together. And this will help us determine how a motor works. And you say to me, John, you've just shown a force on a single bit of current, a coil. How's that going to get a motor which has got bits that turn? And we'll get there. So just let's get the principle in place. And so I want us to make very sure that we've got the idea that these magnetic fields that are created by the permanent magnet and the current carrying conductor, that they will interact to produce the force. Now, we don't want to have to draw those diagrams all the time, so we're going to be investigating different ways to be able to predict what will happen when we place a current carrying conductor in a magnetic field. And so the first thing I'm going to do is I'm going to show you a little simulation where we can go and have a look at what's happening when we place a coil in a permanent magnetic field. So let's go and have a look at this. And you'll see here we've got a horseshoe magnet with a north pole, the red pole at the bottom, and the south pole at the top. We can recognize that the field lines are going from north to south, and we indicated those by those green arrows, and you'll see that's given the symbol B because it's the magnetic field. Now, take a notice that on the side of the screen, there's a hand that is being shown as well. And that hand is showing you that the fingers are pointing in the direction of the magnetic field. It happens to be the right hand. So the fingers point in the direction of the field. Now, if we follow the direction of current, we recognize on the left hand it's the positive direction of current, and on the right hand it's the negative. If we follow it around, we can show the direction of the current as the black arrow that is going from left to right. And that is shown on the hand as the direction of the thumb. So the fingers point in the direction of the magnetic field, and the thumb points in the direction of the current. And if we wanted to be able to use this right hand rule, and it's not the same as the other right hand rule. I call it the right hand slap rule. The unknown in this case is the direction of the force. And the force is going to be in the direction that the palm is facing. So what we recognize here is that in terms of this idea, we can indicate that using the right-hand rule. Now, remember, I'm left-handed, so I'm putting my left hand away. We've got the ideas of the direction of the magnetic field, the direction of the current, and the direction of the force. In terms of the motor, the palm is the unknown, so that will be the force. Have a look at what we're doing here on the board. We're saying the field lines are directing upwards. So they're the green ones. They're going up from north to south. The current is left to right, and the palm is saying this whole coil is actually going to be pushed out of the magnetic field. And so we will see a force. And of course, a force is the indication that there's going to be work done. There's going to be mechanical energy transferred. Because if we get a force on a conductor and we move it over a distance, then that's work. That's conversion of work that is being done there. So just to remind you, in terms of our little rules, we say the fingers are in the direction of the magnetic field. That's the B. The thumb is the direction of the current. That's the I. And the unknown, which is the force, the direction of the palm, is F. So we've got FBI that go together to show us exactly what's happening. Now, the little bit of history around the magnetic effect, I mentioned to you, Fleming was the man that started this. You know what I always like about science, physics or chemistry, is finding different ways to confirm my solution. And Fleming introduced a different rule, a different way of arranging F, B, and I. And so instead of using the slap rule, Fleming uses the left-hand rule. Now, don't get confused. And I'm going to show you a way to remember, a little note not to get confused. When you should use the left-hand rule and when you should use the right-hand rule. You can always use the slap rule. Whether it's motors or generators, you can always, solenoids, single conductors, always you can use the right-hand rule. Fleming's left-hand rule is only for motors. But let's go and see exactly how we're going to use this. So with Fleming's left-hand rule, here's the thing. We're going to arrange the letters in a more traditional way. We're going to say, slap your thigh, you're in the FBI. Okay, so if we look at it like that, F, B, and I. F stands for the thumb, the thrust. So thumb starts with TH, and thrust, which is another word for force, F goes with the thumb. B is for the magnetic field, and that, I say, field with an F goes for the first finger. Okay, so F, B, and I is for the current. Current goes for the second Can you see there's a C in second, so it's FBI, okay? Go through the things on the board here. We've got it very clearly. The thumb is the force. The first finger is going to be the magnetic field, and the second finger, the C there, tells us the current. So always remember, slap your thigh, you're in the FBI, with your left hand. Now, how do we know whether it's left hand or right hand? Well, Fleming, the word Fleming, has an F, an L, and an E. And the word left has an L-E-F. So I make that association. I make that association by saying Fleming has the F, L, and E, and left has the L-E-F. So they must go together. I'll show you another way just now. We recognize now to implement this. We recognize here's the magnetic field, and you can see the field, the first finger, this one, is pointing from north to south. The second finger is giving you the direction of the current. If we placed a conductor here and we said this was from positive to negative, then the current direction is in that direction, which means the force must be up. Now, to be absolutely sure, let's just go and apply this to determining the direction of a little motor. So a motor has those three components that we've spoken about. Here's the magnet, north and south. It has a magnetic field that runs from north to south. We recognize here's the coil in the middle, and it's got the current that is going in on this side, and it's going along that way, and it's coming along that way, and it's coming down that way, and it's connected over here. That's the positive terminal, that's the negative terminal. And so we can draw it through this piece of apparatus, which we're going to show a little bit further. So we've got the field, the current. Which direction is it going to go? Well, let's draw another diagram to make it a little simpler. And we're going to apply Fleming's left-hand rule to that. So here's my diagram. It's cut in half. And we want to have a very clear look at what's going to happen. So we're going to treat each of those parts of the coil as separate conductors. Remember, left-hand rule. So we're going to say north to south. We know that's the first finger. The current goes in. Current comes out. The dot means the current is coming out. So the force must be up. Let's apply it to this side. And what we recognize here, north to south, first finger, current goes in, the force is down. So on that coil, on the one side of the coil is going to go up, and on the other side of the coil is going to go down. And eventually, what we're going to get is a rotation, a movement in a particular direction. But we found it by applying the different rules. Let's just check. Does the right-hand rule work? Yes, it does, in exactly the same way. Remember, the field lines, north to south, current goes into the board, the cross, it's going to go down, the slap is going to go down. Over here, field is from north to south, the current is coming out, the dot tells you the current's coming out, so the force is up. Guys, practice both rules, and you'll see it, they confirm each other. Let's just make sure that you're very prepared to apply those rules and take a careful look at this diagram so you can recognize that in both cases the force is up on this side and the force is down on that side. Welcome back, everyone. We're going to take a more detailed look now at what happens inside an electric motor. We've explored the motor effect, but let's go and have a look at what each of the parts of an electric motor do and how they work together to convert electrical energy into mechanical energy. So, guys, our focus today is really on this process of taking electrical energy and making it mechanical energy, and we are applying the relationship between force, current in a coil, and a magnet. These are the factors that make up, or the parts that make up an electric motor, and in particular we're going to have a look at the direct current electric motor, which always, when you're dealing with direct current, will always have a split ring commutator in it. So what does this thing direct current mean? What does conventional current? Well, let's just remind ourselves. So if we look over here, we'll see conventional current is a term that you've come across. It's the movement of positive charge from the positive terminal of a battery, so the positive terminal of the battery in a circuit, round to the negative terminal of the battery. So the current direction will always be from positive to the negative, the long line being the positive. Direct current tells us that this current is only moving in one direction. So we're not dealing with alternating current. We're not really worried about AC, DC, but only about one direction. And that's not a reference to some music group, but we're dealing with current in one direction. So direct current, one direction, and we will generally take that direction as the direction of conventional current. So make sure that you've got that very clear in your head. So what are the components of a simple motor, a DC motor, a direct current? Well, you'll need a source. The source could be a battery with a positive end and a negative end, a magnet, a coil. Now, the coil inside the motor is called an armature. It's just another name for it, but it's just simply a piece of wire that's looped around inside that space between the magnetic field. And then there's this very important thing. The DC motor has a split ring commutator, and the whole thing also has an axle. Now, guys, the axle is often not shown, but we know that that armature has to rest on an axle for it to spin around. So the coil must be free to spin, must be free to move. Let's take each of those components and let's have a look at an example. So I want to look at a simulation. Here's a simulation of a very simple DC motor. And what you recognize is that we've got the north-south. Notice the magnets are curved, and we'd recognize there's a magnetic field that goes between the North Pole and the South Pole around those magnets, and you'll see they're sort of looped around the magnets. If we look at those green lines, they're kind of looped around the magnets, just like we drew earlier on. And you might recognize we would prefer those to be a bit straighter. And to get them straighter, we're going to need to exert a force. So if we look at what the current direction is, we'll see that the current is moving on the left-hand side of this armature, moving upwards, it's moving into the board. On the right-hand side, it's moving down. And the force then is going to be down on the left and up on the right, which is going to cause it to spin. So I'm going to take this off and I'm going to just allow it to run so that you can see that we can get a motion of the armature in the magnetic field. And that's quite nice to see that. You might be saying, so what's this half loop thing at the bottom? Well, that's the split ring commutator. And we'll have a little bit more to say about that in a minute. So we've seen an example of the DC motor, the simple DC motor. I want to just point out the different parts to that, as we've spoken about them. We recognize this is the permanent magnet, this is the coil or armature, and this part here we would call, this is the source, the battery. This part here is the split ring commutator. Okay, and those are the simple parts of the battery. Now that we've identified the different components of a DC motor, this is just a simple DC motor, let's see how they work together to produce the rotation that we're needing. So I've given a diagram here to explain this process by cutting the coil in half cross-section to show that on this side, where we've got D marked, the current is coming out of the board, where the current is going into the board on that side. So that's the positive end, that's the negative end. Now, if we're wanting to see the rotation, remember we've got two ways of using our hands to be able to determine which direction the force is going to be on these different parts of the coil. And I'm going to use the right-hand slap rule as my first one. So from north to south, I'm pointing my fingers in the direction of the field. At D, I'm noticing that the current is coming out of the board. It's a dot. So that means the force on this end is going to be downwards. So I'm going to indicate that force as a downward force over here. Take a note, at the same time, the field lines are going from north to south, the current is going in at A, and that part of the coil is now going to experience a force that is upwards. Now here, guys, is the very important thing. This coil is one piece of metal. So you can't just have it going up on one side and down on the other, and they separate from each other forever. No, they're one thing. So what happens is they start to rotate. And so our next picture that we're going to get is the picture where A has moved up because it was moving in that direction, and D has moved a little bit downwards. And they're on the axle, so it's starting to move, I hope you can see, in a kind of a clockwise direction. So that would give us the rotation. But hold on, there is a little bit of a problem, and we are going to need to sort that out. I'll explain it as we go along. In our next step, we will get A at the top and D at the bottom. And if we look carefully at the motor, we'll find at that point, because of the split ring commutator, there's no current that is passing through the coil at exactly that moment. So when the coil is in this position, there's no current. And it's just as well. Because as A now moves, it was moving in that direction. Its momentum carries it over, like the momentum of D carries it over, to move into that next section. So it can start to move in that direction. But what I want you to see is the split ring commutator has an interesting effect. At this point, the current now is different in A. There's been a change in the direction of current. A was going into the board on this side, closest to the South Pole. When it's closest to the North Pole, it's now out of the board. And the reason for that is that if we apply our rules, again, we say the field lines from north to south, the current is coming out, it will continue to move down. If it was moving in, it would suddenly reverse direction, and that would make no sense. We want it to be rotating smoothly as it goes along. And so, just to confirm that we've got it right, I want us to use Fleming's left-hand rule as well. And I'm going to apply Fleming's left-hand rule to the part of the coil that's at D. So remember, Fleming's left-hand rule says we take the force for the thumb, We don't know the direction of the force. We're going to work that out. We take the direction of the field for the first finger. So we're going to say north to south. The current is going into the board. That's where the cross is. So we're going that way. And you can see here, the thumb is pointing up. So we are getting a smooth rotation. And so we will eventually come back to the point where the coil is in the original starting point. But part A is on the other side, closest to the North Pole, and part D is closest to the South Pole. And that process cycles all the way around. And what's responsible for that? Well, the reason that happens is because of this device, the split ring commutator. And that's what we're going to have another careful look at and see how this helps a motor actually work. But I think it's time for a short break, so we'll see you after the break when we can investigate in a little bit more detail the operation and the effect that the split ring commutator has in the DC motor. We'll see you soon. Welcome back, guys. We're going to have a careful look at the role of the split ring commutator in a DC motor. Have a look and just at our simulation of our DC motor, and let's get it to run so that you can see that the commutator does definitely rotate in a smooth action. And we recognize that if we were to pause it for a minute, we'd recognize that this region at the bottom here is the commutator. The commutator supplies current to the coil, and it does it in a very clever way. So I want to focus in on that and show you how it changes as the armature rotates from being flat to being vertical, and how the current changes its direction in the armature. So here we go. I've zoomed in on the split ring commutator, and what I want you to see is it has two components. This component here is known as a brush. You think that's a funny word. Why do we have a word brush? Well, actually it's a lot of little metal wires. Imagine a steel toothbrush, and that steel toothbrush is connected to a wire that is connected to the positive or negative terminal of the battery. And so the current will come from the battery into the brush. The brush, there's a little gap. It's not a fixed unit. Over here, there's the cylinder that's in a coil, and that coil is free to move. It's just got contact with the brush, with the bristles of the brush. And so the coil is able to move, and it's able to keep contact with the brushes. And so charge is able to flow through the wires of the brushes into the coil, into the armature. But the most significant part of this commutator is in fact the part that is illustrated over here. It's the split in the commutator. That part, when the brushes are in contact with that gap, no current can go into the commutator, no current can go into the coil. And so there is no current passing through at that point. In reality, this could be a gap, it could be an air gap, or it could be an insulator. But it's important for us to understand. So at this point, how this is connected at this moment, we'd recognize the direction of the current is going to go from the positive through the coil into the commutator, and all the parts of the commutator on this side are going to be attached to the armature. And so the armature at that point is point A, the current is going to go into A. And if we look at the reverse part, we recognize over here the current is coming out of the negative. It's going to come out of D. It's going to convert into the commutator, that second part of the commutator, through the brushes and back to the battery. So that's how this process works, of supplying each part of the coil a different direction of current. So you'll have seen it going in on this side at A, from A to B, and from C to D coming out over there. But as I said to you just now, what the trick is what happens when the armature and the brushes reach that gap point. Well, we'll have a look at exactly what's happening, but let's just make sure we've got the things all lined up. This goes together with the diagram that we showed just now, and we can see clearly the positive direction of current. It's moving in over here, it's moving in over here, it's moving into the board over here, it's moving out of the board over here, just like that. And hence, we'd be able to recognize, using our right-hand slap rule, it's going in on this side, it's going to go up over here, and it's going to come down over here. And as I mentioned to you, what happens when this now moves around, it's moving in that direction, we're going to find that that ring is going to get into a situation where it's in the gap form. And I've redrawn it in this way, just a cross section through, and you'll see that A is now at the top. There is no current going in because the brushes aren't making any connection here. The brushes aren't making any connection over here. So even though the current was going in over there and coming out of there, there's no connection. But the momentum of the motion carries part A across. And because it goes across, the coil moves on as well. And what we recognize is that this part of the coil is now going to be connected to the negative terminal of the battery, and this part of the coil is going to connect to the positive terminal of the battery. And so the direction of the current was 0 at that point, but if we move it on and we wind it on a little bit, we recognize now what's going to happen is this direction is going to be, the current is going to come out over here. And the current over here is going to go in. There's been a change in current because the commutator is now in a different position. So that allows it to carry on spinning. The other important thing that you need to notice, if we didn't have this commutator, these wires connected to parts A and D, if it was spinning very quickly, the wires would get all tangled up and they wouldn't be able to move very freely. So it's a very important part of the DC motor. And you need to understand that it is absolutely essential to keep that rotation going. Now, obviously, we might say to ourselves, well, we've got a simple little motor. Is there a way to make the energy transfer a little bit more effective? And of course there is. We might want to get the motor to spin faster. We might want to get it to, in that way, convert electrical energy into more mechanical energy. And so what are the ways of doing it? The one way is to strengthen the magnetic field. And how you would do that? You would use different magnets. But there's something else that I want to just point out on our diagrams. And we've shown a couple of diagrams, and I want to just use this particular one back here, over here on our apparatus, on our simulation. Do you notice that this diagram is curved, and this one is curved as well? It's done deliberately so that the magnetic field is at 90 degrees as the armature is moving through. It's always at that maximum thrust position. And that's going to be important when we deal with the generator. So we'll come back to that in a little while, but I want you to understand that we can strengthen the field, we can create a curve in the magnet as well, so that at each of these points there's a perpendicularity to where the coil is and where the field is, and the lines are going to make sure that there's maximum thrust. Now, another way of doing it is to increase the number of coils. We've just done one armature, and we've done one split in the commutator. But if you were to open up a little DC motor that could be used in a toy or used in even a simple device, a simple appliance, you will notice that there are lots of little gaps, okay? And that is to show that there are lots of coils. So as the one coil moves out, the other coil moves in, and that also helps to smooth the rotation. So the number of splits in the commutator can increase, the number of coils can increase, and if we do that, we get more current going through, which creates a bigger magnetic field, which creates more thrust. And so what's our summary for today? As we've looked at the motor effect, here are the important things you need to remember. An electric motor transforms electrical energy to mechanical energy. That is the critical idea. Electrical energy into mechanical energy helps us do work. Please remember the difference between Fleming's left-hand rule and the right-hand slap rule. Make sure you've got those clear. Use both of them so you can confirm your predictions. And then remember that a DC motor always has a split ring commutator, and that split ring commutator's role is to change the direction of the current as the coil rotates, to make sure that it's a smooth rotation and there's a free spinning of the armature. And guys, that brings us to the end of our summary, and I just want to make sure that you recognize the detail that we've gone through: the electric motor, the transfer from electrical energy to mechanical energy, and the importance of the force, the coil, and the magnet. Thank you for being with me today. I hope you've enjoyed our exploration as we've looked at the motor effect and the DC motor. From me, so long, we'll see you soon.